Okay, we're going to talk about linear independence. And briefly, linear independence is a property of sets of vectors. And a set of vectors is linearly independent if the vectors in the set point in different dimensions. We have some idea of dimension from our daily life. A plane is two-dimensional, a space is three-dimensional. So linear independence is very much tied up with the idea of dimension. And we'll get more into that in the presentation, some definition and examples. Okay, so let's go through this definition a little bit slowly. So here we have a multiset subset of a vector space is linearly independent if none of its elements is a linear combination of the others. Otherwise, it's linearly dependent. Okay, so let's unpack this a little bit. We're talking about multiset subsets. What's a multiset? A multiset just means you could have duplicates. Okay. For instance, we talked about how 1, 1 is a multiset, but it's not really a set. Set doesn't allow duplicates. Okay, so a multiset subset of a vector space. What we're looking at, a subset of a vector space means we're looking at a set of vectors that lies within a particular space. And that set is linearly independent if none of its elements is a linear combination of the others. So it's kind of a negative definition. Otherwise, it's linearly dependent. That is, as long as we can find one element that's a linear combination of the others, it's linearly dependent. Otherwise, it's linearly independent. We'll see some examples shortly of what's going on here. Okay. All right, now, this equation here expresses the fact that S0 is a linear combination of S1 up to Sn. Okay. So we're going to transform this definition a little bit and see it from a different angle. So here we're starting from this statement, which is the basis of this definition. Again, if S can be written in this way, then S depends on these vectors. S0 is linearly dependent. So we say the set S0, S1, S2, ... Sn is linearly dependent. But we can rearrange this equation here in such a way to solve for S1 or S2 or Sn. So really, when we have an equation like this, we'd have to say that all of these S's are dependent on each other. Or another way of saying it is saying that they're related. And they're related by a dependence relation. Okay, so that's the point here. If we don't want to single out any one of these particular vectors in our statement, we just say that S0 up to Sn are linearly related. Okay, so the point here is that for any of the S's in this statement, where the coefficient C is non-zero, this can be considered as a statement of linear relationship among those S's. So we're going to rephrase these notions in terms of linear relationship. All right, here's a lemma. A subset S of a vector space is linearly independent if and only if among its elements, the only linear relationship of this form. Now notice these vectors have to be distinct vectors, is the trivial relationship where all of the coefficients is 0. Okay, so this is, you can see this is similar to the previous statement. Instead of linear dependence, we have linear relationship, and we want to show that these two ways of phrasing the definition are equivalent. Notice here we have if and only if. That means we have to prove two implications. We have to show that linear independence implies there's a linear relationship. And we have to show that if there's a linear relationship, linear independence means the only linear relationship is trivial. And we also have to show that if the only linear relationship is trivial, then the set of vectors is linearly independent. So let's see what the proof looks like here. Okay. All right, so let's go the first way. Let's first prove that if the subset's linearly independent, that means the only linear relationship is the trivial one. Okay, so if S is linearly independent, then no vector Si is a linear combination of the other vectors. So there's no linear relationship. Another way of saying that would be, if there was a linear relationship, then I could form a linear dependence. And we showed that on the previous slide. If there was a linear relationship like this, if I have a linear relationship C0 S0 plus ... plus Cn Sn, and I set that equal to 0. If I have a linear relationship like this, I can certainly solve for S0 and get a linear dependence like this. I can get S0 as a linear combination of the others, as long as C0 is not 0. Okay. On the other hand, if S is not linearly independent, then some Si is a linear combination of the other S's, and then I could use that to find a linear relationship. Right, so notice what we've actually done here. We've shown that S is linearly independent, implies no linear relation. And then we've shown S is not linearly independent, implies there is a linear relation. All right. So why does this show if and only if? Okay. This statement here that S is not linearly independent implies linear relationship. This is logically equivalent to the statement that there's not a linear relationship implies S is linearly independent. These two statements are called contrapositives of each other. Okay. In the subsequent proofs, we're going to be using contrapositives quite a bit. So if you're a little bit shaky on that concept, I invite you to go to the text. In Appendix A2, it explains the notion of contrapositive. That instead of proving if P then Q, that's the same thing that as if Q is false, then P is false. So read through this example here on Appendix A2 and make sure that you understand the notion of contrapositive. It's really quite intuitive. If you want to say, for example, if we are in Austin, then we are in Texas. That's a true statement. That's the same thing as saying, if we're not in Texas, we're not in Austin. And you can form several if-then statements and find their contrapositive and see that these two things are logically equivalent. So I invite you to do that mental exercise. So the upshot is that we have proven this if and only if statement. A subset's linearly independent if and only if the only linear relationship is the trivial one. Okay. Now, I think it's helpful to have examples in mind of linear independence. So we'll get there shortly and you'll see what's going on. All right, here's an example. All right, so in the plane, these two vectors are linearly independent. Okay, why is that? Well, if I try to take a linear combination, if I try to form a linear relationship between these two vectors, that is, take a linear combination and set it equal to 0, this is a homogeneous equation, and the only way to form a linear relationship among these two vectors is if the two coefficients are 0. Right. So that's exactly what it was saying in the previous statement. They're linearly independent if and only if the only linear relationship is the trivial one. Okay. Here we've shown that the only linear relationship is the trivial one. Therefore, these are linearly independent. Now, think of this in terms of intuition. What you're really saying is 1, 0 points in this direction, 0, 1 points in this direction. And because they point in different dimensions, the only way to add a multiple of this plus a multiple of this and get back to 0 is if both multiples are 0, because they're pointing in essentially different directions. Okay, there's no way to make these two vectors. Remember, you add vectors head to tail. There's no way to add these two vectors head to tail to get back to 0. There's no way to scale these two vectors. For instance, I could scale this vector up and scale this vector down. If I scale this up and this down, the sum is going to be here. All right. That's still not going to give me the 0 vector. The only way to get the 0 vector as a combination of these two is if both vectors multiply 0. Another example. All right, in the vector space of cubic polynomials, P3, the set, actually this should be a square here. This should be a square here. Okay. So here we have two polynomials. These are two elements of the set of cubic polynomials. All right. Now, are they linearly independent? Well, let's try to form a linear relationship. Here's a linear relationship and set the linear combination equal to 0. Now, remember that the sum of two polynomials is 0 if and only if all the coefficients are 0. Now, the coefficient of 1 is C0 plus C1. The coefficient of x squared is minus C0 plus C1. Okay, so the coefficients must satisfy this system of equations. The only solution to this is the solution C0 equals C1 equals 0. Okay, so that means that they must be linearly independent. You can't find a linear relationship that's non-trivial among these two vectors. All right, here's another example. The non-zero rows of this matrix form a linearly independent set. Now, why is this? If you go back to this lemma, we showed that in the echelon form matrix, the non-zero rows form a linearly independent set. So let's go back there and see that. So you can see right here, this lemma, that in an echelon form matrix, no non-zero row is a linear combination of the other non-zero rows. Okay, so that's the same statement as here. No non-zero rows is a linear combination of the others. That means there's no linear relationship among the non-zero rows. Now, of course, we're not including the 0 row, so that's why this holds. Another example of linear dependence, these three vectors. Now, how would I set up a linear relationship among these three? If I call this one V1, this one V2, this one V3, a linear relationship would be a relationship C1V1 plus C2V2 plus C3V3 is equal to 0. Okay, and that's exactly what this system of equations says. This is C1V1 plus C2V2 plus C3V3 is equal to 0. This is just a homogeneous system, so we can solve this and find out that there are more solutions than just the trivial solution. Therefore, these vectors are linearly dependent. Okay, we will be relating the notion of linearly independence to the notion of span. So here's a lemma. Let me fix this up a little bit. Let's say we'll say let V be a vector space. V is a vector space, and S is a subset of that space. And V is an element of vector V is an element of big V. Then S union the vector V, that is the span of S union the vector V, is equal to the span of S if and only if V is in the span of S. All right, so let me give a little illustration of this. Suppose I have a set S of vectors, and here I'll do two vectors like this. This is S1 and this is S2. Okay. Now, consider, now if you think about the span of this set of two vectors, the span is going to be the plane determined by these two vectors. Now, let's take another vector V that's also in the plane. Okay. Now, in this case, V is in the span of S. Okay. And that's the plane. And the span of S union V, well, if I take linear combinations of these three vectors, I'm still going to get the plane. So that's equal to the span of S. Okay. So this is one example. Now remember, this is an if and only if, so really it's two statements. So let me show another example. Suppose I have S1 and S2 in the plane. And suppose V is out of the plane. Okay. Now, since V is out of the plane, V is, in this case, V is not in the span of S. And we'll see a little bit later that the span of S union V is also bigger than the span of S. In fact, the span of S union V will be all of space. So this is not equal to the span of S. All right, so notice that this 2 here, I've shown that V is not in S, and as a result, S union V, the span of S union V is not equal to the span of S. That's the contrapositive of the statement here. Now, if I have V not in S, implies S union V is not equal to the span of S. Remember what I said about contrapositives? That's the same thing as saying that that S union V equals to the span of S implies V is in S. Okay, so here I've shown V is in S implies the span of S union V equals S. Here I've given an example where V is not in S, so that V is not in, V is not in the span of S. V is not in the span of S, so the resulting spans are different, and that's the same thing as proving the implication the other way. All right, so let's go through the proof here. All right, so half of the if and only if is immediate. If V is not in S, then the sets are not equal because V is not in S union V. All right, that was the second example here. If V is not in the span of S, then obviously the span of S union V cannot be equal to the span of S because V is in this set and V is not in this set. Okay, so we've proven in general the example here too. That's a general statement. On the other hand, assume that V is in S. I'm sorry, V is in the span of S. So V is a linear combination of vectors in S. Now, in order to show that S union V, the span of S union V is equal to the span of S, I need to show that these two sets are equal. Now, it's clear that the span of S is contained in the span of S union V because the span of S is the set of linear combinations of vectors in S, which are also vectors in S union V. On the other hand, let W be an element of the span of S union V. Then W is a linear combination of elements of S union V. We can write W as a linear combination in this way. And we can write V as a linear combination of elements of S. So we're using the linear combination of linear combinations lemma that once we replace V with its expression as linear combination of S's, we can have W as a linear combination of S's. That means that W is in the span of S. So we've shown that, in fact, any vector that's in the span of S union V is also in the span of S. So that shows that these two sets are, in fact, equal, and that completes the proof. We have a corollary. If V is in S, then omitting that vector does not shrink the span if and only if it is dependent on other vectors in the set V in S. All right. Now this is a little bit confusing, the logic here, but if you look back here, if you look at this statement here, and here we have S union V equals S if and only if V is in S, we could replace this S union V with S. We can replace this S union V, we could call that S prime. Then this S here is S prime minus V. Okay. If we do that, we actually end up with the same corollary. Okay. So for instance, I could say here, so I would say for the proof of this, so I'll let S prime equal S naught V, and then I would apply, and so that means that S is equal to S prime union V, and I would apply the lemma to S prime. Okay, so really this is just another way of stating the lemma with a different definition of sets. All right. Now, these two subsets of R3 have the same span because this third vector in the first set can be written as a linear combination of the other two. So we apply the lemma. That means that the two have the same span. Okay. All right, a set S is linearly independent if and only if for any V in S its removal shrinks the span. All right. This is just the contrapositive of this corollary. This corollary actually has two statements from the if and only if. If you follow through these two statements, if and only if, that gives us the contrapositive of these two statements. Okay, so these two corollaries are essentially equivalent. Okay,